Hello, my name is Andy Goldschmidt, and I'm here to introduce you to the bilinear dynamic mode decomposition for quantum control. This work was done with Kaiser, Steve Brunton, and Nathan Kutz at the University of Washington, and Jonathan DuBois at Lawrence Livermore National Lab. So what we're going to need to do today is talk a bit about how we're going to get from dynamic mode decomposition to bilinear dynamic mode decomposition. And the way we're going to do that is introduce DMD, or the dynamic mode decomposition, and its extension to linear control systems, DMDC. What we're going to require for quantum technologies are incredibly exacting. This forces us to pursue data-driven methods for quantum control and system identification. And this leads us to introduce something like the dynamic mode decomposition, which is a data-driven, model-free regression framework for system identification. And what this means is that DMD doesn't have any physical assumption describing the data when it goes in. It's completely independent of the underlying physics. And so instead, what we're going to be working with is a list of observables at a specific time. And so we're going to call this a snapshot, sort of a photograph of measurements. And we're going to assemble these snapshots into two matrices that are offset by a single time step. We're then going to look for the best linear propagator to describe the dynamics of these observables in these measurement spaces. And it's this that we're going to pursue via the DMD regression, in which we're going to look for this best propagator via the pseudo-inverse of the data matrix X. Now, DMD isn't going to compute this matrix A. Instead, it's going to look as an algorithm for the best modes and eigenvalues associated with this system. But there are a lot of adaptations and adaptations, and the critical one for us is the dynamic mode decomposition for control. So what we can do is we can take control inputs, which we know, and treat those as another snapshot matrix, and then apply a DMDC regression to find not one but two operators associated with this system to solve the control problem. Now for quantum dynamics, we'd like to do something like DMDC. And in quantum mechanics, a snapshot is going to be a list of expectation values of observables, which we create from an ensemble of quantum experiments. Now in quantum mechanics, a state is sort of a way to assign probabilities to a list of observables. And in quantum mechanics, this list of observables is generated, its dynamics are generated by a linear operator. So this is exactly what we ended up doing with DMD. We had a list of observables, or snapshot, and dynamics which were generated from some linear operator. And this connection in classical mechanics is called Koopman-von Neumann theory. And there's a lot of literature exploring the ways that DMD fits into this picture. For us, what this means is that we have to be very careful about the kind of quantum control equation that we're going to be using. That is, the form is going to influence the kind of DMD that we have accessible to us. And quantum control dynamics, it turns out, are bilinear. And so what this means is that we're going to have to adapt DMDC to accommodate the bilinear equations of our list of observables. This leads us to pursue the bilinear dynamic mode decomposition, in which we'll construct a nonlinear term from the inputs and the outputs via this Cauchy-Rao product, which basically is just a Kronecker product that respects the time dimension. The bi-DMD regression then finds the best linear control model associated with our system. And now the bi-DMD is going to inherit the same advantages as DMD and DMDC. That is, it's going to be fast, interpretable, and easily adapted. And it's informed by the underlying physics of quantum mechanics. So if you'd like to learn more, check out our paper in the New Journal of Physics, or my GitHub for some code about this stuff.